Hello, today we're going to start a new series on quantum mechanics concepts, and we're going to start with Dirac notation and its simple application to polarization of photons. Before I start, you are about to see some weird notations, and when I first encountered them, I asked myself two questions, which you yourself might be asking. The first is, why are we using this most bizarre and peculiar form of notation to represent quantum mechanics? And the only answer I think I can come up with is because it works. Because it actually spectacularly represents faithfully what you see in experiment. And I'll show you how. The second question I asked myself was, well, given that's the case, who ever thought that this weird form of mathematical representation might conceivably represent the experimental outcomes of quantum mechanics experiments? And the answer to that, I think you have to say, is, well, that's the definition of a genius. Only someone who was really brilliant, like Paul Dirac, would have been able to see that you could represent quantum mechanics in this way. So I'm going to begin by starting with the notation and a little bit of the mathematics. For quite a while we're not going to do any physics at all. We're, as it were, just going to get our chess pieces out so that we understand what the notation is in mathematical terms, and then we will consider how that is reflected in understanding the physics. So notation and maths first. There is a thing called a ket vector. It is denoted in that way. That is called a ket. There is an associated vector where you'll notice the brackets are the other way round, and that is called a bra vector. I'm afraid Dirac wasn't very creative. The reason he had a bra and a ket is if you put the two together, you get bracket. Not very inventive. The ket vector, which we represent, as I've said, by A, can also be represented as a column of numbers. A1, A2, A3, all the way down to AN, where N is the number of dimensions you might be considering. All this will become clear when we look at the physics. But in terms of pure notation, in terms of pure mathematics, it's a series of numbers which can be complex numbers. I'll explain what I mean by that in just a moment. On the other hand, a bra vector, which you remember is the other way round, is represented in almost the same way, except that it is a row rather than a column. It still has the numbers A1, A2, A3, all the way up to AN, but those numbers are what's called complex conjugated. And I'll explain exactly what I mean by that. In fact, I better do that now. Firstly, what is a complex number? A complex number, which we sometimes write as Z, is equal to a real number, that can be any number you like, x, plus the imaginary number times a real number, y, where an imaginary number is the square root of -1. So called because there is no such thing as the square root of -1. There's no solution to the square root of -1. It is imaginary. So a complex number consists of a real number plus another real number but multiplied by the square root of -1. And the two, of course, do not easily combine. Now you can represent a complex number on what's called the complex plane, which is essentially a graph. We would normally call this the x-axis and this the y-axis. But what we now do on a complex plane is we call this the real axis, that's where the real number will be shown, and this is the imaginary axis. So if we have a vector that is x plus iy, that means that we show x, which is the real number on the real plane, or the real axis, and we show y, which is the value of the imaginary number on the imaginary axis, and that means that the actual vector itself, z, will equal x plus iy. That's the way we represent it. So z equals x plus iy. And you can see that the modulus of z, that is to say the actual length of this vector, and I'll say squared, is equal to, by Pythagoras, that is simply going to be this squared plus this squared, which is x squared plus y squared. So the modulus, or in other words the length of the vector, which is the combination of the real plus the imaginary part, is simply said by simply given by Pythagoras. Now I mentioned a thing called a complex conjugate, which we denoted by putting an asterisk above the number. That means the complex conjugate of z. And what is this weird thing? Well, it couldn't be simpler. It's simply the same value of x, but you change the sign of the imaginary term. So if z is x plus iy, the complex conjugate is x minus iy. And you can, I think, fairly easily see that the complex conjugate of the complex conjugate, if you do it twice, that will be you change the sign again and you get back to where you started. So the complex conjugate of a complex conjugate is the number you started with. And I can represent this complex conjugate also on the complex plane. X remains the same, so the x dimension will be the same, but the imaginary term has changed signs. So now we are going to be at minus y, and consequently the vector z complex conjugate is going to be denoted in that way. You'll notice that the modulus, the length of this vector squared, is still going to be x squared plus y squared, because you're going to get x squared plus minus y all squared, and minus y all squared of course is plus y squared. So the modulus of z and the modulus of z star, or the complex conjugate of z, is always going to be x squared plus y squared. But I want to draw your attention to something rather interesting, which is that if you multiply z by its complex conjugate, you're going to get x plus iy multiplied by its complex conjugate x minus iy. And what you're going to get there is x squared. The plus iyx will cancel the minus iyx. And so you're now just going to be left with iy times minus iy, which is minus I squared y squared. But I squared is minus 1. So minus I squared is plus 1, and that will give you plus y squared. The complex number times its complex conjugate gives you the same result as the modulus of that number squared. The modulus of z squared was x squared plus y squared from Pythagoras, but you get the same result if you multiply the number by its complex conjugate. And that will be important when we get to some of the physics of quantum mechanics. I hope you will see that if z is just a real number, e.g. 2, then z star also equals 2, because you only change the imaginary term. You change the sign of the imaginary term. If you don't have an imaginary term, there's no sign to change. So the complex conjugate of a real number is just the real number. Now we need to consider what happens if we add these vectors. So let's say we've got a vector, this is a ket vector A plus a ket vector B. That's going to produce a ket vector C. And the way it works quite simply, I'm going to use 3 dimensions to save a bit of time. So we're going to have A1, A2, A3 plus B1, B2, B3. What is that going to produce? Well, it couldn't be easier. It's going to be another ket vector, and you simply add the dimensions. So A1 plus B1 becomes the first term in the ket vector. A2 plus B2 becomes the second term, and A3 plus B3 becomes the third term. So this is one whole number because you've added these two together, so you get another ket vector with 3 dimensions. The important thing about all of this that you'll notice is that you must always use the same number of dimensions. It's no use adding a three-dimensional ket vector to a two-dimensional ket vector. That is not going to work. You always have to work in the same number of dimensions. I happen to choose 3 for illustration purposes. Now for very basic multiplication, let's say that we're going to take a number, which could be a complex number, multiplied by the ket vector A. We're going to see that that will produce another ket vector, and that of course is simply going to be alpha times, well, A, again I can represent in 3 dimensions, A1, A2, A3, and that couldn't be easier. You simply multiply alpha on each of these terms to give you a new ket vector, which is alpha A1, alpha A2, alpha A3. So whatever that number, whether it's a real number or complex number, you simply multiply each of the individual terms by that number, and that gets you the new ket vector C. Now we come on to what will turn out to be a very important concept when we get to the physics. And that is what happens if you multiply a bra vector by a ket vector. So we've got bra vector A times ket vector B. That is called an inner product. And it's kind of equivalent to a dot product if we were simply talking about ordinary vectors. And the way you work it out is you write out the bra vector, and you remember I said that the bra vector is a row vector where all the elements are complex conjugated, and we now know what that means, multiplied by the ket vector, which of course is a column vector, but this will be B1, B2, B3. And what that produces is not a vector, just a number. And the number is produced by taking the first element in each case and multiplying together, then adding the multiple or the product of the second elements, and then add the product of the third elements. I'll say that again. It's the product of the first elements plus the product of the second elements plus the product of the third elements. So that will be A1 star times B1 plus A2 star times B2 plus A3 star times B3. That just becomes one number. It's a complex number, but it is just a number. It is not any longer a vector. Now suppose I had asked us to do BA instead of AB. I think you will see that through kind of similarity, what you will get here is B1 star A1 plus B2 star A2 plus B3 star A3, because these will just be reversed. If I now take BA and I complex conjugate it, I will get B1, because the complex conjugate of a complex conjugate gets you back to where you started, times A1 star plus B2 times A2 star plus B3 times A3 star. But that is the same as that, because the order of the numbers doesn't matter. And so we've just shown that AB is equal to BA complex conjugated. Now I must introduce you to a matrix. We're still doing the maths here. We haven't got on to any physics yet. I'm going to introduce you to a matrix. It's a square matrix. It can have any dimensions, but I'm going to choose 3 dimensions simply to make life easier. And a matrix you write with curly brackets, and it will have a row and a column. The rows M11, M12, M13. The second row M21, M22, M23. And the third row M31, M32, M33. And you'll notice that essentially I've got I rows and J columns, and each element can be written as Mij. So if you take this element here, it's the second row, first column, so it's Mij, M21. take this element here, it's the third row, it's the second column, M32. That's the way you actually identify the elements of the matrix. Each of those elements, each one of these values, can be a complex number, and we know what that is. Now, I can create a complex conjugate of that matrix, which we call M star, and guess how I do it? You're absolutely right. We simply take the complex conjugate of each element in the matrix. So I've now got to write out each element, but for each one I simply put a star, meaning that each element of the matrix has been complex conjugated. We know what that means. It means that the imaginary term changes sign. So here is the matrix, here is the complex conjugate of the same matrix. In other words, Mij has become Mij star. And just to remind you again what that means, that if the complex number is x plus iy, then the complex conjugate becomes x minus iy. Now I'm going to introduce you to the transpose of the matrix. All you do here is you interchange rows and columns. The diagonals stay the same, but the matrix essentially flips over. So the rows become columns and the columns become rows. So MT now becomes M11, M21, M31, as opposed to, you'll notice it was M11, M12, M13. It's now the other way round. Then this becomes M12, M22, M32, and this becomes M13, M23, M33. That's what's called a transposed matrix, or if you like, the more general term is to say that Mij has become Mji. You've just interchanged the rows with the columns. You'll notice, however, that the diagonals remain the same. M11, M22, M33, M11, M22, M33. But these two numbers have interchanged. They transpose positions. Those two numbers have transposed. Those two numbers have transposed. It's a kind of mirror image about the diagonal. Well, now I must introduce you to another matrix, which is called M dagger, and that is a combination of these two. It's both a complex conjugate and a transpose. So first of all, we have to take the transposed matrix, which is M11, M21, M31, M12, M22, M32, M13, M23, M33. That's the transpose matrix, that's just that. And now we complex conjugate every term. And we know what that means. So that is now what's called the complex conjugate of the transpose, which we represent as M dagger. So in other words, what's happened here is Mij of our original matrix has become Mji complex conjugated. And now we consider a situation where M, the matrix, equals M dagger. And let me give you an illustration. If M is equal to, and I'm only going to do a two-dimensional matrix here to save time. This is the matrix. It's got 4 elements, 2 rows, 2 columns, 1, 1 plus I, 1 minus I, and 3. What is M dagger? Well, remember, M dagger, you have to transpose about the diagonal and complex conjugate. The diagonal doesn't change. So the 2 elements of the diagonal don't change, and anyway, they are not complex numbers. 1 plus I has to move down to here, but it also has to be complex conjugated, so it becomes 1 minus I. The 1 minus I has to go up to here, but it has to be complex conjugated, so it becomes 1 plus I, and you'll notice that M equals M dagger. When that happens, the matrix is called Hermitian. That means that the matrix is equal to its transposed complex conjugate. I'm afraid we need to continue with the maths a little further, because now we want to ask what happens if we have a matrix and we apply it to a ket vector. Well, we can write that out. I'm going to do this in 2 dimensions to save time. So M11, M12, M21, M22. That's the matrix. The vector is A1, A2. And if you multiply that out, you will get another ket vector. That's the key point. And the way you get it is you take this number times that number plus that number times that number. That's the top line. And then this number times this number plus this number times that number is the bottom line. I'll do that again. This number times this number plus this number times that number is M11 times A1 plus M12 times A2. That's the top. That's all just one number. So that's the top of our new ket vector. And this one is that number times that number, which is M21 A1, plus this number times this number, M22 times A2. And that's a new ket vector because there's just one number at the top, one number at the bottom. This is just an addition of 2 very likely complex numbers. But nonetheless, what essentially you've got from the action of a matrix on a ket vector is just a new ket vector. I need to introduce you to what is called the identity matrix. And the reason it's called an identity matrix is that it has the numbers 1 on the diagonals and 0s everywhere else. So I'm going to do a 3-dimensional matrix, but you'll easily see how to create any dimensions. The diagonals have 1s, everything else is 0, and that is called the identity matrix, or sometimes called the unit matrix. Not to be confused with the unitary matrix, which has the following properties: that if you take the unitary matrix and multiply it by U dagger, which you will remember is the transposed complex conjugate of U, that gives you the identity matrix. In other words, you can consider that U dagger is the inverse of U. So when you multiply U by U dagger, you essentially get the identity matrix. Then I need to explain to you what a determinant is. If we want the determinant of matrix M, we write that with straight lines rather than with curly brackets. And if the matrix is made, I'm going to do a 2 by 2 matrix, A, B, C, D, where A, B, C and D will all be complex numbers. The way you calculate the determinant is it's A multiplied by D minus B times C. For 3 dimensions it's a little bit more complicated, but we're not going to need that for the time being. So let's just stick with 2. You multiply the 2 terms on the diagonal and subtract the product of the 2 terms on the off diagonal. And you can see immediately that the determinant of the identity matrix, which of course would in this case be 1, 0, 0, 1, would be 1 times 1 minus 0 times 0. The determinant of the identity matrix is 1. Now I need to introduce you to the trace of a matrix. And the trace of a matrix, if the matrix is A, B, C, D, then the trace of a matrix couldn't be easier. It's just the sum of the elements on the main diagonal. So in this case it will be A plus D. If it were a 3 by 3 matrix, you just add all the numbers on the main diagonal, and that is called the trace. And you'll be delighted to know that we've almost come to the end of the notation and the mathematics, and we will soon be able to get on to the physics. There's just one more thing to explain, so bear with us. You'll remember that we showed a thing called a Hermitian matrix. That was when the matrix equals its transposed complex conjugate. And where you've got a Hermitian matrix, which I will represent with the sign H, you can act on a vector, a ket vector, A to produce the self-same vector A, but multiplied by a number. Not a vector, not a matrix, just a number. It might be a complex number, but in this case it will be a real number. So it will have no complex, it will have no imaginary term. And that is going to prove to be one of the most important equations in the whole of our quantum mechanics dealings. So what we're saying in maths terms is that a Hermitian matrix acting on a vector produces the same vector but now just multiplied by an ordinary real number. And when that is the case, that vector is called an eigenvector, and that number is called an eigenvalue. What you will typically find is that that self-same Hermitian matrix may operate on a different vector to produce the same different vector but multiplied by a different real number. And what you will say is that for each Hermitian matrix they will have two separate eigenvectors, each of which will give rise to a separate eigenvalue. That's the maths. Now we can move on to the physics. And what the physics says is that the Hermitian matrix represents a measurable or an observable, something that you're going to actually measure. The eigenvectors represent the possible states of the system, and the eigenvalues represent the actual results you get when you make the measurement. I hope all will become clear when I do some examples of this in a moment. I want to consider some of this by considering the issue of polarization. Now, we covered that in one of the videos in the series on electromagnetic radiation. And amongst other things, we said that if you take unpolarized light and you send it through a polarizer which will polarize vertically, that's how I will represent a polarizer that will polarize vertically. You send unpolarized light through this polarizer. When it comes out the other side, it will be vertically polarized. If you then send it through another polarizer, which is also vertically polarized, then all of the light in this section will get through. 100% of the light that is polarized gets through the vertical polarizer and comes out the other side, because the polarizer is in the same direction as the light that is polarized. It all goes through. By contrast, if we take exactly the same experimental setup with our vertical polarizer and we send it through a polarizer, this is now polarized in the vertical direction, we now send it through a polarizer that is horizontal, then absolutely nothing gets through. This is experimentally verifiable. You've got polarized light in vertical direction. Will it go through a horizontal polarizer? Not at all. And then the final example we just use is that you take unpolarized light, you put it through the vertical polarizer, out it comes vertically polarized, and now you put it through a polarizer which is polarized at 45 degrees. And what do you find? You find that 50% of the intensity of the light that was coming towards this polarizer comes out the other side. So whatever the intensity is of the polarized light here, 50% of it comes out the other side. That's what we learned from the video on electromagnetic radiation. That is all experimentally verifiable. More generally, we said that if you put this light through a polarizer in the vertical direction so that it comes out vertically polarized, and then you then put it through a polarizer which is at an angle theta to the vertical direction, then the intensity of the radiation that comes through that second polarizer will fall off according to cos squared theta. In other words, when theta is naught, that is to say the polarizer is in exactly the same direction as the original polarizer and the polarized light, when cosine theta is naught, when cosine naught equals 1, when theta is naught, cosine theta is 1, cosine squared theta is 1, 100% of the light comes through. When theta is 90, cosine 90 is naught, cosine squared naught is naught, none of it comes through. So the intensity of the radiation falls off according to the angle between this polarizer and this polarizer. But I said that there was a bit of a problem with this in terms of dealing with it solely classically mechanical, because the intensity of radiation is proportional to the E field squared. And this might be taken to suggest that if the intensity falls off as the cosine squared term, if intensity goes down, that must mean that the E field goes down, and that means that the total energy goes down. Now the total energy, you know that the energy of a photon is given by Planck's constant times the frequency. So that suggests that if the energy is going down, since h is a constant, the frequency must be going down, and that suggests that the light will change colour. But in fact that's not true. What happens is if you send blue light, polarised here, less blue light will go through. The intensity of the blue light will change by cosine squared theta, but the colour won't change. So this can't be entirely right. And what we're now going to look at is the quantum mechanical concept, which says, and I'll just give you a brief overview, what happens is that this unpolarized light consists of lots of photons. Some of them will get through this first polarizer and some of them won't. The ones that get through will be polarized vertically. When the photons get to the next polarizer, again, some of them will get through, some of them won't. The ones that do get through retain the same frequency of the radiation. It's just that fewer of them get through. Consequently, the total intensity reduces because the total number of photons that gets through reduces, so the total amount of energy that gets through reduces because each photon contains a certain amount of energy, and if fewer of them get through this second polarizer, then there will be less energy overall that gets through, but the frequency of the radiation doesn't change. Now we're going to look at that from a quantum mechanical point of view using the concepts that we developed earlier in this video. And if you ask me the question, why do we do that? The answer is because it works. So I'm going to consider polarization horizontally as being the x state represented as the x ket vector, and I'm going to call that 1, 0. Now I'm conscious that I haven't explained why I've done that. That will come later. For the time being, let's just get some general concepts out so you can see how it works. I'm also going to consider vertical polarization, and I'm going to call that the y ket vector, and that is going to be represented as 0 and 1. Now I'm going to introduce that term that I said would be very important, and that is the inner product of x and y. And this turns out to have a very important physics meaning. What it means is, if I prepare light in the y state, that is to say, I prepare it in the vertically polarized state, what are the chances of it going through an X polarizer, that is, a horizontal polarizer? Now we already know the answer to that. If you prepare it in the vertical state and try and put it through a horizontal polarizer, nothing will get through. So we know the answer experimentally, and we know the answer classically. So this has got to come up with the same result. And what we say in physics is that the inner product of x with y, that is, you prepare it in y and you try to put it through x, that whole term is what is called the probability amplitude. Not the probability yet, it's the probability amplitude. To get the probability, you have to square it. Or to be absolutely precise, you have to take the probability amplitude and multiply it by its complex conjugate. Remember, we showed that yx is the complex conjugate of xy. Now, as it happens, you'll notice that there are no complex numbers in these vectors. So for the time being at least, this nuance will not be a worry to us. All we need to do is to take the inner product and square it, and we get the probability. Why is this inner product the probability amplitude? And why is the square of the probability amplitude the probability? There is no way of proving that. That was a quantum mechanics principle or a concept. I think it was developed by Max Born, who simply asserted it. And the point is, it actually accords with experiment. And that's why we use it. So this is a very important term. As I've said, you prepare in y and you try and put it through x. And we know the answer must be 0 because there's no chance of a photon that is vertically polarized going through a horizontal polarizer. So let's see if that works. So how do you take x, inner product of x with y? Well, you take x and you make that a row vector, so that's 1, 0. You should actually complex conjugate it, of course, but there is no imaginary number, so there's nothing to do. And then you multiply it by the y vector as a column vector. And you know what the rule is? It's that times that plus that times that. So it's 1 times 0 is 0, plus 0 times 1 is 0, gives you the answer 0. And of course you now need to square it. So 0 squared is 0. So the probability of a photon prepared in the y axis, which is the vertical axis, going through a horizontal polarizer is 0. So far it works. Well, let's do a few more tests. Suppose you prepare it in the x frame and you send it through an x polarizer. That is to say, you polarize it in the horizontal direction and you send it through a horizontal polarizer. Well, that's kind of the equivalent of this here, except that these are two verticals. If they're both horizontal, the light will go through. 100% will go through. The probability will be 1. Is that true? Obviously, remember, to get the probability we need to do the square. So that's going to be, well, x is 1, 0. So that's going to be 1, 0 times 1, 0. This should be complex conjugated. I will keep saying this, but there's nothing to do a complex conjugate because there's no complex number. So now you get 1 times 1, which is 1, plus 0 times 0, which is 0. 1 plus 0 equals 1. 1 squared is 1. And so we've shown that if you prepare in the x or the horizontal polarization and you try and put it through a horizontal polarizer, 100% will go through. Well, let's, for completeness, just check that the other one works. If you prepare it vertically and try and get it through a vertical polarizer, what's the probability of it going through? Well, we know the answer. That's 100%. Will it work? Well, what is the y? Is 0, 1. So this is going to be 0, 1, which I'll say again should be complex conjugated, but there's nothing to do, times 0, 1. 0 times 0 is 0. Plus 1 times 1 is 1. That gives you 1. 1 squared equals 1. 100% of photons prepared in the y frame, which is the vertical polarization, will go through a vertical polarizer. And if we look again at this equation where we did the inner product of x with y and we got 0, that is no chance of anything in the y, that is the vertical polarization going through a horizontal polarizer. What we are saying, if you get a result 0, you can say that x and y are what is called orthogonal. That is to say, they are completely inconsistent. If it's in y, it definitely won't go through x. If it's in X, it definitely won't go through Y. Now I want to remind you about another equation that we developed that I said would prove to be very important, and that was a Hermitian matrix acting on a vector A gives exactly the same vector A multiplied by a real number, where that number is not a matrix, it's not a vector, it's just a number. And I said that you could assign physical meanings to these. H, the Hermitian matrix, becomes the operator or the measurable or the observable, the experiment if you like. The eigenvector is the state the system can be in, and lambda is the result that you get. So let's say that I have an experiment which I will call H, and I'll put a little circle there, which means what I'm about to measure is either the vertical or the horizontal polarization of a photon. For the time being, we're going to ignore all other directions. It's either horizontal or it's vertical. And I'm going to act on the X eigenvector. And you remember that X was the horizontal polarization, and we represented it, I'll just put it over here, we represented that as 1, 0. I didn't tell you why, that will come later. Now what I am asserting is that if you've got a Hermitian matrix acting on a vector, you will get the same vector multiplied by a number. So we expect to get a number multiplied by X. And the question is, do we do so? Well, I will need to tell you what this matrix is. Again, I'm going to tell you, I'm not going to derive it, but we will illustrate a derivation of it later on. For the time being, I'm just going to tell you that we can represent this Hermitian matrix, which is the operator or the measurable, as it's a 2 by 2 matrix, and it couldn't be simpler. Well, I suppose it could, but not by much. That is the Hermitian matrix, which is the vertical or horizontal measurement. So what I've got to do is to apply this to the X eigenvector and see if I get the same eigenvector with a number in front of it. Well, let's see. So we've got 1, 0, 0, minus 1. That is the Hermitian matrix, the operator, acting on X. And X is 1, 0. And now you've got to remember your matrix times vector multiplication rules. It's 1 times 1 plus 0 times 0 is the top number. Well, 1 times 1 plus 0 times 0 is 1. And then for the bottom number, it's 0 times 1 plus minus 1 times 0. Well, 0 times 1 is 0. Minus 1 times 0 is 0. That's 0. That vector and that vector are exactly the same, which is what we expected to get here. What is the number in front? It is simply plus 1. It is a number, it is a real number, it is simply plus 1. So we've taken this general term here, where we've got eigenvectors and eigenvalues, and we've shown that if we use this operator, which is the measurable, and we apply it to the X eigenvector, which is represented like this is the horizontal state, you get plus 1 times the original state. Now let's see what happens if we apply it. This is the self-same operator, so we're still going to use this matrix, but we're now going to apply it to the Y vector, and we should get lambda, a different lambda of course now, times the Y state. Or do we? Well, here we go again. H, the Hermitian matrix, is once again 1, 0, 0, minus 1. But this time, Y, you may remember, is 0, 1. That's what I gave you. That's the vertical, that's the state representation of the vertically polarized photon. Well, what does that give us? Again, it's going to give us a vector. You take 1 times 0 plus 0 times 1. Well, that's 0. And then you take 0 times 0 plus minus 1 times 1. That's minus 1. And that is not equal to that. But I can quickly make it equal to that. I just put -1 in front, and then I convert that to +1. And then -1 times 0 is 0, -1 times 1 is -1. So effectively I've now got exactly the same eigenvectors here, but the number in front is now -1. So I've got a situation that when I apply this matrix, this measurable, this experiment, onto the x eigenvector, which is the horizontal, I get an eigenvalue of +1. When I apply the same observable onto the y eigenvector, I get the same eigenvector back, but with an eigenvalue of -1. So if you like, h is the observable, and the only observable is this photon, or is this beam of light polarized vertically, or is it polarized horizontally? The states for horizontal and vertical polarization are given like this, and the result of the experiment, is it horizontal or is it vertical, are given by the eigenvalues +1 or -1. Now you could look at it like this. You could have an experiment, a sort of a kit, a piece of kit. We don't know what's inside that piece of kit, but it tests to see whether light is vertically or horizontally polarized. I mean, the best way of doing it, of course, is simply to have a vertical polarizer. And then if the light goes through it, and behind it you would have, say, a light-sensitive diode or some light-sensitive device. And if the light goes through it, since it can only, for the time being, the conditions are it can either be vertically polarized or horizontally polarized. If the light that hits this polarizer goes through, it must be vertically polarized. If it doesn't go through, it must be horizontally polarized. And what we can do on this piece of equipment, we can have two lights, a red light and a green light. And the red light comes on if the light goes through the polarizer, which means it must be vertically polarized. And the green light comes on if the light doesn't go through the vertical polarizer, which means it must be horizontally polarized, because those are the only two directions that at the moment I'm allowing. So if you like, the piece of equipment, which is the measurable, is H. The states of the light coming in, that is these eigenvectors here, represent whether the light is actually vertically polarized or horizontally polarized. And the eigenvalues, which are +1 or -1, are really just, does the red light come on or does the green light come on? They are different, and it's the red light and the green light which are the true results of the experiment. You cannot measure H. You cannot directly measure the state. The only thing you can do is to look at the result. Did the red light come on? Did the green light come on? And they are represented by the eigenvalues. And I've prepared this little chart here, which I shall flash up from time to time to remind us of where we're coming from. This is the basic equation. The Hermitian acting on an eigenvector produces a number multiplied by the same eigenvector. Above this, I've written down what the mathematics says. You've got a Hermitian matrix acting on an eigenvector. It produces the same eigenvector and a real eigenvalue. Below, I've put what that means in the physics. In the physics, H represents the observable or the measurable, the experiment. A represents the possible state of the system. There will always be two or more, otherwise the thing becomes trivial. In the example I've just given you, there were two, vertical or horizontal. That will produce the same state but multiplied by a number, and that number will change depending on whether the system is vertically or horizontally polarized. And indeed, that number is represented by the experiment as whether the red light or the green light comes on. So this representation of quantum mechanics has worked so far, but we've got a lot further to go. So now let's do a little bit more of a test. This time I'm going to take unpolarized light and send it through a vertical polarizer. So of course it will come out vertically polarized, there's no question about that. And now I'm going to send it through a second polarizer, which is at the 45-degree angle, and it's the forward slash 45-degree angle. And the question is, what will come out the other side? Well, classical mechanics already tells us this. Whatever the intensity is of the light that is in the vertically polarized state here, it will be half of that that comes through. The more general case, as we showed, was it's cos squared theta. In this case, theta is 45 degrees. The cosine of 45 degrees is 1 over root 2. Cos squared theta is 1 over root 2 squared, which is a half. So classically, we already know the answer. Whatever the intensity of the polarized light, what will get through the polarizer, which is at an angle of 45 degrees, is half of that intensity. And here we can pause and wonder at the weirdness of quantum mechanics, because what we're actually saying in quantum mechanics terms is that this polarized light consists of photons. If this is monochromatic light, that is, it's all the same color, say red light, all those photons will have the same energy, because we know that the energy of a photon is h times the frequency, and if the frequency is common because it's the same color, red, then all the photons have the same frequency. All the photons are polarized vertically, so all those photons are absolutely identical. And here's the weirdness of quantum mechanics. When they get to this polarizer, half of them will go through and half of them won't. And there's absolutely no way of telling which half will and which half won't. You can only say that there's a probability that any photon arriving at that polarizer has a 50% chance of getting through. 50% of them will, 50% of them won't. And the only thing you can say about that is that that is weird. But having accepted that it's weird, we now need to work out what the representation of a forward slash 45 degree state is. We've already said that we've got the x state, which is the, remember, horizontal state, and we said we have a y state, which is the vertical state. So you might think that we can represent the state, which I'll put like this, the ket vector of the 45 degree forward slash state. You might think that you could represent that as simply a combination of the x state and the y state, because of course it's got a bit of both. It's got an upward, it's got a vertical dimension and it's got a horizontal dimension. So it could be just the combination of the two. But I will show you that that is not going to quite work. It's not far short, but it's not going to work. Why is it not going to work? Well, let's just work out what that would mean. Well, the x component, remember, was 1, 0, and the y component was 0, 1. And I told you how to add vectors. You just add the two top numbers and the two bottom numbers. So that would give you a representation of 1, 1. Nothing wrong with that, you might say. But I now ask the question, what is the probability if I prepare my photon in the 45 degree angle polarization? What is the probability of it going through a 45 degree angle polarizer? And we all know the answer to that. It must be 100%. If you prepare it polarized in that direction, it will go through, certainly, a polarizer polarized in that direction. So, and remember, that's the probability amplitude. To get the probability, we have to take the square. So, let's see what that amounts to. Remember, we've just assumed, as it turns out it'll be wrong, but we've assumed that the forward slash state can be represented as a 1, 1 vector. Well, to do the inner product, we have to do 1, 1 multiplied by 1, 1. That's 1 times 1 plus 1 times 1 is 2, but we have to square it, and that gives us 4. So there's a 400% chance that a photon produced in the 45 degree forward slash direction will go through a forward slash polarizer. You cannot have a 400% chance. It can only be a 100% chance. So we have to do what's called normalize. We have to adjust this so that when we do this calculation here, we get 1 instead of 4. And the trick is that you simply make the forward slash state equal to x divided by the square root of 2 plus y divided by the square root of 2. And if you use x and y divided by root 2 in each case, then this will become 1 over root 2 naught, this will become naught and 1 over root 2, and when you put that into this equation you will get the number 1. It's called normalizing. It just ensures that whenever you do the inner product of identical vectors you get 1 and not the absurd answer 4. Okay, so just to recap, we have established that the forward slash state can be represented as x plus y divided by the square root of 2, where remember x was simply given as 1 naught and y is given as naught 1. So in other words, x over root 2 will mean that you've got a 1 over root 2 and a naught, and y over root 2 will mean you've got a naught and 1 over root 2. So the next question is, what then is a 45-degree angle polarizer that's a backslash at 45 degrees? And let's take a guess, which turns out to be right, that it is x minus y over root 2. And if you substitute these two in, if you do the inner product of backslash with backslash, you will indeed get 1, which of course is the acid test that this will work. So let's just calculate what the actual vectors are going to be in their matrix, in their sort of column vector form. The forward slash is going to be x over root 2, which is 1 over root 2 naught, right, from this is x over root 2 is 1 over root 2 and naught, and the y is going to be naught and 1 over root 2. And remember, the addition is you just add the two top numbers and you add the two bottom numbers, so that's going to give you 1 over root 2 and 1 over root 2. So the vector representation for a forward slash is 1 over root 2 and 1 over root 2. If you want the backslash, well, we've already shown what that is. It's x minus y over root 2. X is going to be 1 over root 2 and naught, minus now naught 1 over root 2. So that's going to be 1 over root 2 minus naught is 1 over root 2. Naught minus 1 over root 2 is minus 1 over root 2. So the column vector representation of the backslash at 45 degrees is 1 over root 2 and minus 1 over root 2. So now we better do the acid test and see if quantum mechanics is going to succeed. What is the probability if I prepare the photon in the forward slash state? What is the probability that it will go through a polarizer in the backslash state? Now those two polarizers are at 90 degrees. So we know the answer. Nothing will go through. Consequently, the probability amplitude, which is this, and the probability itself, which will be the square of this, must be 0. That's what we've got to hope for. Okay, let's see if it is. What is the backslash? Well, the backslash is this term here, and we put it as a column vector. 1 over root 2 minus 1 over root 2. It should be, I'll keep saying this, it should be complex conjugated, but there's no I terms, so there's no imaginary terms to complex conjugate. Forget about that. Multiplied by, or taking the inner product with the forward slash, which is this one. 1 over root 2, 1 over root 2. And how do we calculate that? We take that times that plus that times that. Well, 1 over root 2 times 1 over root 2 is a half. minus 1 over root 2 times 1 over root 2 is minus a half. That equals 0. And of course we have to square it. It still equals 0. Quantum mechanics is still working. The probability of preparing a photon in a forward slash position at 45 degrees and getting it through a backslash at 45 degrees polarizer remains at 0, which is what we'd expect. And we've already shown that if you prepare it in a forward slash and you try and put it through a forward slash, it will be 100% of the time. Okay, so let's see if we can test it a little bit further. We take our unpolarized light and we put it through a vertically polarized polarizer. It comes out, it's vertically polarized of course, and now we put it through a forward slash polarizer. And the question is, what proportion will go through? What's the probability the photons will go through? We already know from classical mechanics, 50%. Now we ought to be able to do it with our inner product. So what's our inner product? Remember, you prepare it on the right and you test to see if it'll go through on the left. That of course is what's called the probability amplitude, and to find the actual probability you have to square it. And that should come to a half, which of course is the equivalent of 50%. So that will be equal to, well, the forward slash, remember, was represented as a 1 over root 2, 1 over root 2, and that has to be in row form, so 1 over root 2, 1 over root 2, multiplied by the vertical vector, and remember the vertical vector was represented as 0, 1. So let's do the calculation, and what do we get? 1 over root 2 times 0 is 0, plus 1 over root 2 times 1 is 1 over root 2. But we have to square it. And 1 over root 2 squared is a half. Yet again, the formalism is working. We have worked out the probability of preparing in the vertical case and trying to get it through an polarizer which is angled at 45 degrees. We know classically there's a 50% chance, or at least 50% of the intensity gets through. Quantum mechanics tells us that there is a half, which equates to 50% of the probability of a photon prepared in that state getting through a polarizer in this state. Now I need to tell you the Hamiltonian for the two types of forward slash backslash. Those are the two options now, and the Hamiltonian is given, I'll give it to you, I'll have to show you why in a future video, is actually 0, 1, 1, 0. So once again we've got that famous equation which I prepared here, that the Hamiltonian times the eigenvector is equal to a number times the eigenvector. So when we take this Hamiltonian and multiply it by a state, we're going to get a number multiplied by the state. So let's try it. The Hamiltonian, I've told you, is 0, 1, 1, 0. Now I'm going to apply this to the forward slash. And the forward slash is 1 over root 2, 1 over root 2. And that is going to give me another vector. Well, what vector does it give it? Well, to get the top number, it's 0 times 1 over root 2 plus 1 times 1 over root 2, which is 1 over root 2. And the bottom number is 1 times 1 over root 2 plus 0 times 1 over root 2, which is 1 over root 2. Those two are the same, and the number, once again, is plus 1. And let's do it the other way. Let's take the Hermitian matrix for the forward and backslash measurements. And this time we'll apply it to the backslash, which you'll remember was 1 over root 2 minus 1 over root 2. That's going to come to 0 times 1 over root 2 plus 1 times minus 1 over root 2 is minus 1 over root 2. 1 times 1 over root 2 plus 0 times minus 1 over root 2 is plus 1 over root 2. That is not equal to that. But I can very easily make it equal to that simply by putting a minus 1 in front and then multiplying this by minus, so the minus becomes a plus, and this by minus, and now you've got that that is the same as that, but the eigenvalue is -1. This is the equivalent of my red light and my green light. I take my piece of equipment, which is my, as it were, measurable. I apply it to one of two different states. If it's this state, you get a +1, which means the red light comes on. If you get this state, you get a -1, which means the green light comes on. We'll continue with more examples of this in the next video. This may seem a very complicated way of stating the very obvious. Indeed, we could have done virtually all of this using classical mechanics, and it would have been easier too. But as we shall see, it's a very powerful way of describing quantum states and outcomes which, and this is the key point, are probabilistic rather than deterministic. To see that that will produce another ket vector, and that of course is simply going to be alpha times, well, A, again I can represent in 3 dimensions, A1, A2, A3, and that couldn't be easier. You simply multiply alpha on each of these terms to give you a new ket vector, which is alpha A1, alpha A2, alpha A3. So whatever that number, whether it's a real number or complex number, you simply multiply each of the individual terms by that number, and that gets you the new ket vector C. Now we come on to what will turn out to be a very important concept when we get to the physics. And that is what happens if you multiply a bra vector by a ket vector. So we've got bra vector A times ket vector B. That is called an inner product. And it's kind of equivalent to a dot product if we were simply talking about ordinary vectors. And the way you work it out is you write out the bra vector, and you remember I said that the bra vector is a row vector where all the elements are complex conjugated, and we now know what that means, multiplied by the ket vector, which of course is a column vector, but this will be B1, B2, B3. And what that produces is not a vector, just a number. And the number is produced by taking the first element in each case and multiplying together, then adding the multiple or the product of the second elements, and then add the product of the third elements. I'll say that again. It's the product of the first elements plus the product of the second elements plus the product of the third elements. So that will be A1 star times B1 plus A2 star times B2 plus A3 star times B3. That just becomes one number. It's a complex number, but it is just a number. It is not any longer a vector. Now suppose I had asked us to do BA instead of AB. I think you will see that through kind of similarity, what you will get here is B1 star A1 plus B2 star A2 plus B3 star A down to AN, where N is the number of dimensions you might be considering. All this will become clear when we look at the physics. But in terms of pure notation, in terms of pure mathematics, it's a series of numbers which can be complex numbers. I'll explain what I mean by that in just a moment. On the other hand, a bra vector, which you remember is the other way round, is represented in almost the same way, except that it is a row rather than a column. It still has the numbers A1, A2, A3, all the way up to AN, but those numbers are what's called complex conjugated. And I'll explain exactly what I mean by that. In fact, I better do that now. Firstly, what is a complex number? A complex number, which we sometimes write as Z, is equal to a real number, that can be any number you like, x, plus the imaginary number times a real number y, where an imaginary number is the square root of -1. So called because there is no such thing as the square root of minus 1. There's no solution to the square root of minus 1. It is imaginary. So a complex number consists of a real number plus another real number but multiplied by the square root of minus 1. And the two, of course, do not easily combine. Now you can represent a complex number on what's called the complex plane, which is essentially a graph. We would normally call this the x-axis and this the y-axis. But what we now do on a complex plane is we call this the real axis, that's where the real number will be shown, and this is the imaginary axis. So if we have a vector that is x plus iy, that means that we show x, which is the real number on the real plane, or the real axis, and we show y, which is the value of the imaginary number on the imaginary axis, and that means that the actual vector itself, z, will equal x plus iy. That's the way we represent it. So z equals x plus iy, and you can see that the modulus of z, that is to say the actual length of this vector. Hello, today we're going to start a new series on quantum mechanics concepts, and we're going to start with Dirac notation and its simple application to polarization of photons. Before I start, you are about to see some weird notations, and when I first encountered them, I asked myself two questions, which you yourself might be asking. The first is, why are we using this most bizarre and peculiar form of notation to represent quantum mechanics? And the only answer I think I can come up with is because it works. Because it actually spectacularly represents faithfully what you see in experiment. And I'll show you how. The second question I asked myself was, well, given that's the case, who ever thought that this weird form of mathematical representation might conceivably represent the experimental outcomes of quantum mechanics experiments? And the answer to that, I think you have to say, is, well, that's the definition of a genius. Only someone who was really brilliant, like Paul Dirac, would have been able to see that you could represent quantum mechanics in this way. So I'm going to begin by starting with the notation and a little bit of the mathematics. For quite a while we're not going to do any physics at all, we're as it were just going to get our chess pieces out so that we understand what the notation is in mathematical terms, and then we will consider how that is reflected in understanding the physics. So notation and maths first. There is a thing called a ket vector. It is denoted in that way. That is called a ket. There is an associated vector where you'll notice the brackets are the other way round, and that is called a bra vector. I'm afraid Dirac wasn't very creative. The reason he had a bra and a ket is if you put the two together, you get bra-ket. Not very inventive. The ket vector, which we represent, as I've said, by A, can also be represented as a column of numbers. A1, A2, A3, all the way down, and I'll say squared, is equal to, by Pythagoras, that is simply going to be this squared plus this squared, which is x squared plus y squared. So the modulus, or in other words the length of the vector, which is the combination of the real plus the imaginary part, is simply said by, simply given by Pythagoras. Now I mentioned a thing called a complex conjugate, which we denoted by putting an asterisk above the number. That means the complex conjugate of z. And what is this weird thing? Well, it couldn't be simpler. It's simply the same value of x, but you change the sign of the imaginary term. So if z is x plus iy, the complex conjugate is x minus iy. And you can, I think, fairly easily see that the complex conjugate of the complex conjugate, if you do it twice, that will be you change the sign again and you get back to where you started. So the complex conjugate of a complex conjugate is the number you started with. And I can represent this complex conjugate also on the complex plane. X remains the same, so the x dimension will be the same, but the imaginary term has changed signs. So now we are going to be at minus y, and consequently the vector z complex conjugate is going to be denoted in that way. You'll notice that the modulus, the length of this vector squared, is still going to be x squared plus y squared, because you're going to get x squared plus minus y all squared, and minus y all squared of course is plus y squared. So the modulus of z and the modulus of z star, or the complex conjugate of z, is always going to be x squared plus y squared. But I want to draw your attention to something rather interesting, which is that if you multiply z by its complex conjugate, you're going to get x plus iy multiplied by its complex conjugate x minus iy. And what you're going to get there is x squared. The plus iyx will cancel the minus iyx. And so you're now just going to be left with iy times minus iy, which is minus I squared y squared. But I squared is minus 1. So minus I squared is plus 1, and that will give you plus y squared. The complex number times its complex conjugate gives you the same result as the modulus of that number squared. The modulus of z squared was x squared plus y squared from Pythagoras, but you get the same result if you multiply the number by its complex conjugate. And that will be important when we get to some of the physics of quantum mechanics. I hope you will see that if z is just a real number, e.g. 2, then z star also equals 2, because you only change the imaginary term. You change the sign of the imaginary term. If you don't have an imaginary term, there's no sign to change. So the complex conjugate of a real number is just the real number. Now we need to consider what happens if we add these vectors. So let's say we've got a vector, this is a ket vector A plus a ket vector B. That's going to produce a ket vector C. And the way it works quite simply, I'm going to use 3 dimensions to save a bit of time. So we're going to have A1, A2, A3 plus B1, B2, B3. What is that going to produce? Well, it couldn't be easier. It's going to be another ket vector, and you simply add the dimensions. So A1 plus B1 becomes the first term in the ket vector. A2 plus B2 becomes the second term, and A3 plus B3 becomes the third term. So this is one whole number because you've added these two together, so you get another ket vector with 3 dimensions. The important thing about all of this that you'll notice is that you must always use the same number of dimensions. It's no use adding a 3-dimensional ket vector to a 2-dimensional ket vector. That is not going to work. You always have to work in the same number of dimensions. I happen to choose 3 for illustration purposes. Now for very basic multiplication, let's say that we're going to take a number, which could be a complex number, multiplied by the ket vector A. We're going